Simulation, very important topic of chapter 4. We learned to talk about simulation. We learned to, it's a bit off the point maybe, but still related, the error propagation thinking, where we could get some formulas on how errors propagate through nonlinear systems. We already knew how errors propagate through linear systems. They do that additively by the variance rule. But through nonlinear systems, we would have to, if we need to work with it, we would have to work with approximate rules. That's the error propagation rule. But then we could do alternatively. We could base such considerations on simulation. Now, either seen as a probability tool, or when we use it for statistics, when we use simulation for statistics, we often call it bootstrapping. Bootstrapping comes in two different versions, basically. The one based on certain parametric models, that is, assuming normal or exponential. The good thing about it is that we can assume any kind of distribution that we believe would be the right one, not only the normal. We could extend our toolbox with all other sorts of distributions. That's pretty strong, actually. And then even more strongly, to some extent, with other limitations it also comes with, but at least the idea is pretty strong, that we can do statistics without any assumptions of distributions at all, which seems like a nice idea, right? Because then, hey, why use assumptions if we risk they can be wrong? That's one of the sensitive areas of classical stats, actually. This is this problem of assumptions potentially being wrong, and where the field is sometimes a bit challenged about how to deal with that level of uncertainty, actually. Nevertheless, we can sometimes work with no assumptions of distributions and then do statistics by resampling the data itself, right? That's the idea of non-parametric bootstrapping. That when I compute a coefficient of variation, then I resample my data again and again with replacement, and then many times I compute such a coefficient of variation that gives me a distribution. I could either plot or I could extract the quantiles. And that's kind of a simulation of the uncertainty of what's going on, right? Instead of finding theoretically a sampling distribution, I simulate the sampling distribution and look at it. So I use the computer simulations to do the uncertainty evaluations with no probability theory involved, or just a little bit maybe. So that's a pretty strong tool. You were given 4 specific versions in method boxes of bootstrapping in the material, all of them dealing with 1 and 2 sample situations. You were also told that the idea is much more general than that. It can be used for any kind, also in regression and you name it. But hey, we have to stop somewhere. So we give it very explicitly to you in 1 and 2 sample data. And then we give you the 2 different versions, either the parametric or the non-parametric. That gives 2 by 2, 4 different versions of essentially the same thing. Really strong tool. Bit too much. Well, it's a bit difficult to see the R code there, right? Well, with good eyes, it's visible. That's good enough. Well, not for 10 of you, of course, but for most of you.